Let me rewrite this maybe in the volume. So in general, for homogeneous isotropic body, we have all the stress-strain relations, in 3D, okay? In 3D elasticity. And this is specific for homogeneous isotropic. So class, I repeat, this basic relation you should know. And I think many of you, remember well, it is always first related to sigma x, no Poisson ratio. Then only we have the Poisson ratio effect. The stress in y direction will cause negative strain in x directions. And the positive stress in z direction will cause negative strain in x directions. And let me finish this. This is the basic one. So positive stress in x direction will cause negative strain in y directions. Then you have a direct one, because direct stress is going to cause positive stress in y is going to cause positive strain. And then positive stress in z direction is going to cause negative strain in y directions. This is the so-called Poisson ratio effect. Then the same thing, just I write it down here. Plus this. Okay. And then you have the gamma xy, tau xy over g, gamma xz, tau xz over g, gamma yz, tau yz over g. This is in general 3D. X, Y, and Z. Now when we go to specializations 2D, what we mainly cover is what is the characteristics of problems that you can classify as 2D, and what are the types of 2D problems that we have. Okay. So we start with plane stress. So for plane stress, I think the characteristics is the one particular direction is very small compared to the other two. In this case, I have the x direction, I have the y direction, and I have the z directions. So z directions is the thickness is very small relative to compared to x and y. So this is one of the characteristics of plane stress problem, and we have loading only in the plane where the body lies. So we only have loading in xy plane, and we don't have loading on the top surface and the bottom surface, even in x and y direction. So this top surface and bottom surface there's no loading acting, okay? But the loading act through the thickness. It can be uniform, it can be non-uniform, but if the thickness is small, then we can consider that as uniform. So these are the characteristics of plane stress problem. The plane stress problem is sigma z equal 0. Okay. Sigma z equal to 0. This is the characteristics of plane stress problem. And because of the geometry and the loading, the only non-zero stress that we are interested in that will be these three. This is a non-zero stress. And correspondingly, of course, we have deformation, so you have the strain. XY. Okay. These are non-zero and non-zero stress and the corresponding non-zero strain. Okay. But we must remember that sigma z is equal to 0, but then our epsilon z is not equal to 0, meaning that if this is the z directions, then in plane stress problem, you have change in dimension. in thickness here. You have change in thickness, which is caused by sigma x and sigma y. Okay. So we need two equilibrium equations in x and y to solve this problem, and we need these stress-strain relations, three stress-strain relations to solve for sigma x, sigma y, tau xy with this coordinate system. Okay. And there is three strain displacement relations that relate the three strain to the two displacement. Okay. Displacement, you have u and v. So u is the displacement in x direction, v is the displacement in v directions. Now, the question is now, I think by Metam, what is the, how do we get the relations between the three stress and the three strain for plane stress problem is we start with sigma z equal to 0. Okay? Sigma z equal to 0. So eventually, what we need for stress-strain relations will be, if we express sigma x, sigma y, tau xy equal to some matrix multiplied with epsilon x, epsilon y, gamma xy. Okay. So this is the three stress-strain relations that we need for plane stress problem. Okay. And how do we get this? If we start from here, because these relations is easy to remember. You can also have the stress-strain relations in 3D relating. You put the stress here and the strain on this side. Okay, but that stress-strain relations will be about a bit more difficult to remember, because to remember this is easier because we can work from the first principle of the effect of stress in the 3D body. So if we start from here, then what we need here is, this is the non-zero strain relation that we need. This is the relations that we need. And this is the relations that we need. So in plane stress, we don't need this. This is, so we don't need this. So we don't need to consider them. And in plane stress, we need to relate these three to this, or this stress to this. So we need to look at this equation, these equations, and because this equation is appearing here, and these equations is relating the sigma x and sigma y. Okay. So let's see how the process. I show you the process. I will not be able to go through the whole thing. Okay. So let me see how I can. So the first relations that you have is, of course, these relations, and then this becomes 0. So you have epsilon x equal to this and z 0, and then epsilon y. And this one becomes 0. And this third one, z is equal to x. And the last one is this. Okay, then next. So these are the relations that we have in 3D elasticity that we need, okay, for plane stress problem. Now, if we want to relate we need to try to take this as take this out to become the, we need to solve these two equations in order to get what is the relations between sigma x, sigma y, and epsilon x and epsilon y. Okay, these two relations where we make sigma x, we solve these two equations, then we get what is sigma x, and we also, and then correspondingly, once we know what is sigma x, you can get what is sigma y by substituting back into any of the equations. Okay? So that is how we get to the stress-strain relations if we start from this basic, if we start from this basic strain equal to this, strain y is equal to this, and strain z is equal to this. Okay? So these third relations, actually, we do not need these in the derivation process, but this one is to let us know in plane stress problem, this is non-zero because you have Poisson ratio effect, meaning that physically we have, if you pull here, you pull there, then the third direction, which is perpendicular to the plane x and y, will have change in dimensions. This tau xy is straightforward because tau xy can be just written as a g gamma xy. Right? And the g is have these relations. So these third relations we already have. Only these two we need to solve these two equations simultaneously. So we need to, from these two equations, solve for sigma x and sigma y in terms of epsilon x and epsilon y. So that is the process and how we get the stress-strain relations for plane stress problem if we start from here. Okay. Is it clear for you, Madam?
Thank you, Prof.
Thank you, Prof.
You can try this. I think you have to try it out. I think solve these two equations simultaneously. Okay. Okay. Now, if we go to here, of course, sometimes because whatever we get from here, then in order to factor out some common terms here, then we play around with whatever we want to factor out, so the content inside will change. But to get the basic relations, if you have this and this plus this. So that is for plane stress. For plane strain, for plane strain problems, okay, if we have a plane strain problem, then what we have will be plane strain. So plane strain, typically we have a body which is of constant cross section, then we have it very, very long in one particular directions. So we have here, then there is all the cross section, they are the same. Then you will have it in one dimension very large compared with the other two. So if I can draw here x, here x, and here y, okay? X, y, and we have a z here. So if this is the case, then we are going to have x, y, and z. And this one of the dimensions is very long compared with the other two. And furthermore, if you take any of the section out here, they are all the way the same. Yeah? All this section never change. And the loading also from one end to the others, they never change. They are the same. And the loading only stay in the XY plane. Okay? And the loading never change from one side to the other, and they stay only in XY plane. Okay? So that is the characteristic of plane strain problem. And the other characteristic is there is a very rigid surface on either end here. There's a very rigid surface on either end of this very long body where it prevents. Very rigid means there is no change in length. There's no change in length of this body in the direction where it is very large. So for that reason, plane strain problem, epsilon z become 0. Epsilon z becomes 0 because of these two rigid body, and you do not have any forces which will cause any change in length in this direction. And because this is rigid, so the length never change. But consequently, you are going to get, because this you have the stresses acting in x and y directions. Of course, due to Poisson ratio effect, it will try to make the third direction, which is z direction, expand. Okay, it will cause also the effect on the third direction because of the Poisson ratio effect. But if this is prevented from moving, which is why we have epsilon z 0, but you have stresses in x and y direction, it will cause this structure tends to expand in the other direction, z direction, but you prevent it from moving. That's why we have sigma z not 0. Okay. It tries to expand, but if you let it expand, then you don't have the stress. But if try to expand in this direction or contract in this direction, but we don't allow it because of the rigid surface that we assume here. As a result, we have stresses, okay, which is different from plane stress. Plane stress just now is sigma z equal to 0, but epsilon z not equal to 0. So these are the particular. This is the characteristics of this plane strain problem. And plane strain problem, we solve plane strain problem because the geometry are all the same from one side to the others. The loading are also the same from one side to the others. Okay. So we solve this by taking one slice out of this. We solve this problem by taking one slice out of this. So this one will become 1 unit length and subjected to loading. So whatever that we obtain from one particular slide anywhere here, then it will represent the whole structures. Okay, so it can represent the state of stress in the whole structures. So that is plane strain. So because of the nature of the problem and the loading applied is uniform from one end to the others, I think, and we solve this by taking one slice out like this. So the non-zero stress, which is of interest to us, in plane strain problem is also sigma x, sigma y, and tau xy, and the corresponding strain. Okay. Okay. Displacement also the same. And W equal to 0 because of these two phi, which is assumed for the characteristics of the plane strain problem. So we have 3 stress, 3 strain, and 2 displacement to be solved. 2 equilibrium equations. We have 2 equilibrium equations, 3 stress strain relations, and 3 strain displacement relations that we need to make use of. So the stress strain relations that we need is also this. But then the content here will be different because of the conditions of plane strain, which is different from plane stress. So how do we get these relations from these 3 basic ones? Again, we go back to this. Now this is 0 now. Okay, this is 0 now. This is 0 now. So from these relations, we can get sigma z in terms of sigma x and sigma y, and then substitute back into here. Okay. So that is, let me go a little bit one more time. So now let me take away this. So the equation that we need to derive the stress strain relation will be this. There is this terms here that we appear here, which is for plane stress is non-zero, so we need to consider. And for this also same thing. Okay. Then we need this gamma x. We need this. We need this now. Okay. Plus, of course, the same thing like plane stress. We make use of this in order to get we want. So remember, what we want is this. If we get stress equal to something multiplied with the strain. Hope you can see here, or it's already missing part there. Yeah. What we want is so again, we need to be able to use these two equations, then consider this. Okay. This one in plane strain is epsilon z equal to 0. So when we put epsilon z equal to 0, then from here you get minus this sigma x E minus this sigma y over E plus sigma z over E equal to 0. So from here you get sigma z over E equal to, can you still see this? Okay, sigma z over E equal to, then you can get it from here, nu over E sigma x plus sigma y. And you just bring this to this side, then you get, so this is why sigma z is not 0 here. Then this one has to be substituted into here, sigma z over E, sigma z over E, which is in terms of sigma x and sigma y only. So at the end, you get epsilon x, epsilon y. Consider this here in terms of sigma x, sigma y. Then again, go through the process, try to solve these two equations, already change everything to sigma x and sigma y in terms of solve for sigma x, then get also what is sigma y, then you can get the equations for, you can get the equation for a stress strain relations for plane strain. Okay. So that is the process. Okay, that is the process. Okay. Any questions on this process of getting the stress strain relations, particularly for 2D problem? Plane stress, plane strain, using this basic relation. Any questions? Okay, so there's a question from. Okay, so how can you get the governing equation? So Ahmed, actually, I will go to that when I go to the specialization of 1D. Okay. This is called shear strain in plane strain. Okay. Shakur, what is your meaning of your question? Shear strain in plane strain? Okay. How you write shear strain in plane strain? Okay. Shear strain in plane strain, plane strain problem, the shear strain that we are interested to solve is this. In shear strain in plane strain, also you have the shear strain that we are interested to solve for is gamma xy. Gamma xy is shear strain. Okay. So this is just, it is a shear strain. It's just the shear stress divided by G. So this is how we write the shear strain. It's the same like the original equations. Same like the original equations of stress strain relations in 3D, because yeah. Abdul Shakur, okay, shear strain in plane strain. This is a shear strain in plane strain, which is similar to the one in the 3D case. Okay. Arun, can I get the value? Can you get the shear value strain without G? No, you cannot get the shear strain without G, because if shear strain, of course, if you know the stress, then if you want to know the shear strain, you need to know the G. Okay, but remember, gamma xy also is a distortion of infinitesimal element. So we can make use of the geometry aspect, which is one element in xy plane. And when it is distorted, then we have change in angle of that element. So we can also get, if we derive it from the point of view of changing in shape and relate that to the change in angle. Okay? So in that way, you can get the shear strain without G. You relate to the change in the geometry. change in geometry, then you can get the shear strain without necessity to know the material properties of the G. Okay. So Harun, the question is, can I get the value of shear strain without G? You can get the shear strain without G if you relate that to the change in shape. So if you can measure the change in shape, and especially if you can know the change in angle in XY plane or YZ plane and XZ plane of an element, then you can get the shear strain. Let me pause here before I go to the next one.